Hey, what's going on, guys? xiangqi here. In this video I'd like to demonstrate how to create a recursive function with a whole lot of local variables, with an argument, with a depth argument, and the function would eventually return a value. So first of all, let me demonstrate the C source code for the program that I already have. So this is the chess program that relies completely on unsigned integers that I'm currently porting from C to 652 assembly. I'm doing this by hand because that's my interest, basically. I could have used the compiler, obviously, but for instance, the CC65, I guess that's the name for compiler. It doesn't actually do what the compiler is meant to be doing in terms of putting the local variables onto the stack frame. So it does this a little bit different. It just emulates stack frames somewhere else in the memory. I read about that once. I'm not sure about how exactly that works in CC65, so I'm not going to be talking about that. Instead, I'm going to be talking about the current implementation I have here. So let's consider the following function just to give an idea of what exactly we're going to be doing here. So you can now ignore all the variables before the search function. We don't need them. They are not involved within the program. So we have a function that takes depth as a parameter. So this is the first essential thing to consider. So here is our search function, and this function eventually returns a best score. Now the best score is a local variable, here it is, that is defined in the search function. Apart from the best score, we have up to 11 variables here that are going to be used in this function in order to generate the moves, evaluate the position, find the best move, and associate the best source and the best target score with the best score. And eventually we can rely on that to make to initialize the absolute best source and best destination with this temp source and temp destination. Eventually these values can be, since they are global, here they are, so then they can be used to actually make a move on a board. We don't I don't yet have that in 652 assembly. And yeah, so I'm making this for King1 with the King1 emulator I made, and here I just, by the way, I've updated this the code editor, so now I'm using reusing code mirror, and I've slightly changed the highlighting so it now supports the 652 nicely. So and the very last essential thing is actually the recursive call itself. So here is the recursive call. And please know that here we have this depth -1. So before calling this function recursively, we need to decrease the depth. So let's just focus on these three major points. So function definition, maybe four, yeah, not three, maybe four. So function definition, local variables definition. Then we have this recursive call, decreasing the depth. Meanwhile decreasing the depth, right? And then eventually we have to return a certain value. So let's focus on this part. Now let's go back to my assembly code here. So what we do here is I'm clearing the decimal flag just to make sure that subtract works properly. And now one of the interesting things, I'm using the A register in order to keep track of the search depth. I do store the search depth on the stack later on because I'm going to be reusing the A register. Obviously, you want to use A register all along the way. But anyway, eventually, I'm relying on the A register. So not eventually, initially, I'm relying on the A register to specify the depth for our search. So 3 stands for search depth, and yeah, by the way, here I just can say that this is the search depth, and then I'm jumping to this subroutine search, and then when I return from here, I just stop. So before anything else, before trying to explain what exactly I'm doing here, all this whole lot of things, I'll now do a very simple thing. I would now just by the way, actually, I don't really need to, yeah, okay, let me just comment out all the stuff that regards to the recursive function call. So now what it's going to be doing is just a regular function. So just call search, pushes some data to stack, then pulls it back, and yeah, and then return should bring us here, and then it should be showing 208 hexadecimal. So let's actually try to run this. So just assemble, upload 0200 is the origin, and Control G to run the code. So we just ran the program and we just returned. Again, before diving into this, how this works, I just want to demonstrate you that, let's have a look at this hex dump as well. So yeah, before even looking to the hex dump, before looking to the hex dump, I just want to show you 00F2. So the stack pointer, so this is the machine context dump. F2 in particular shows us where the stack pointer is pointing to. So FF is the top of stack. So we just have a look at the memory dump. So from page 2 basically, or yes, better to say page 1, I believe. So from 100 hexadecimal to 200 hexadecimal. So this is the stack page for K1, right? So what we have here, you see this FF. This comes from the fact that we did actually initialize it and pushed. No, this reference is not on the cards really, but just to give you an idea. So eventually we have returned, and now stack pointers points to the very top, like here. And these values are coming from the KMROM, so because in order to see something, you're like in the ROM loop sort of. So that's the reason for this system function calls are firing, and they are put on the stack every time. That doesn't matter now, really. Now, the next thing to consider, and you saw like it was just kind of done once. So now I assemble, upload 0200, run, and it seems like it's exactly the same, but now this function worked recursively like 3 times calling itself. So before showing the hex dump, let me just quickly show what it does. Again, like we're not touching the local variables for now. So search, then without much explanation for now, we're just decreasing by 1 the depth, and then search again. And we do this until depth is not equal to 0. But once the depth is equal to 0, we're branching to return. Then we pull back all the local variables, and then we return. So now how to make sure that this actually works, yeah? So if we have a look at the memory dump again, then already you can see that we have up to 3 frames with the local variables. So here comes the first one. Well, actually, it's been a little bit malformed and smashed of some sort. Anyway, I just want to show you that we have this 3 FFs, which are coming from the manner that I'm initializing the best score with the minus infinity value. But the actual number is not 12 here. So it's just 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, it's only 10. So I'm not really sure why is that happening. And is that the case? Well, probably it is, because if we still have a look at the stack pointer, it's 00F2. It still points to FF, which means that everything is just all right. Now, some debugging stuff. So by the time I'm gonna be adding some code just to show some debugging information, I would be explaining what exactly it's doing. Yeah, so yes, that's probably, so again, like, just a little bit spoiler ahead. So this ugly piece of code stands for creating the local variables, and I believe there is a better way, like just shifting the stack pointer to the desired amount of values, and where needed I just can actually do this initialization, and probably they're going to be working exactly the same, but since I didn't yet test that, I'm not going to be claiming that here. And it's important to restore the stack pointer, like to push it back. Well, and since we don't probably even need the pools here, because we're not much returning here anything at the moment we don't much return anything. So probably just adjusting the stack manually would work here as well. But probably, yeah, probably that would be in the next video already, not in this one at the very least. And now, interestingly, that once we created a whole lot of local variables that are needed for image generator and generally for a search engine to work, we currently have the stack pointer where we have, and just to give an idea, if I just break right over in here, for instance, upload. So now this should initially start, yes, and stop at before the very first recursive call here. So 0 to 0 0, and now the stack points to F1. Oh my god, that was explosion. We have a war here in Ukraine. Don't forget about this. Oh crap. Okay. Yeah, I'm sorry, just when this stuff explodes outside, I'm losing my thought a little bit. Okay, so break, and now let's have a look at the machine context. So here, 00F1 is where the stack pointer is kind of pointing to, so 00F0, 00F1, so it should be somewhere here. And again, like the dump of the memory might be a little bit different from the dump of the machine context, because machine context is being dumped just before the ROM drops to the state where it can already provide that information. So this dump is the actual state of the machine, while this one is the information for debugging. So they a little bit like different, I would say. Okay, but anyway, what do we have here? So here we already have this 03, which stands for a depth, because you remember, like, the very first depth, the very first parameter to push was the depth. So 00F1, and if we just add 12 to it, which I point out here, so stack pointer plus 12, so 0F0, F1 plus 1, 2, 3, 4. By the way, plus 1, stack pointer plus 1 is, like we have here, the best score. So this is how we can reference the local variables. This is very essential. So once we've pushed all the variables onto the stack, the matter of referencing those, so I just can add an offset to this where the stack pointer is pointing to get the value that regards to the current stack frame on the current depth. So for instance, if we want to reference the best score, I just need to say stack pointer plus 1. So here is the stack pointer points to F1, right? So F0, 01 F0, 01 F1. So F1 plus 1 is going to be FF, which is the best score, which it is because we did initialize it with FF. So I hope this is pretty self-explanatory. Then the rest are zeros because we just initialized all the variables with the zeros here. Yes, we've initialized all the variables with the zeros here. And here, the very first thing to push onto stack is the search depth. So here the search depth was 3. Okay. I'm sorry guys for this environmental sounds, just the bombs exploding out there, can't do much about it. So the A register, which is the depth, was equal to 3, and here, yeah, by the way, it's in, yeah, it's almost midnight, and they are firing there. Oh, right. So this depth gets stored onto the stack, hence this 3, right? So how this makes sense. And now our goal is, because after we have made a register, so after a register is no longer equal to 3, so now it's 0, then it's FF, so it might be changing no matter how much times. So we need to restore, we need to load the depth back to the A register. In order to that, we need to reference the local variable depth that is stored onto the stack. And this is stored as stack pointer plus 12. So stack pointer plus points here, 01 F1 and plus 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And here we have our 03. So what we do here, so this is quite interesting. So I'll now get rid of this break. So actually we broke here. So the next thing, what we're gonna be doing here. So TSX stands for transferring the stack pointer value to the X register. So stack pointer at this point is equal to F1. You remember this. So points here, and the value of F1 after this instruction is executed. The value of the X register is equal to F1. Then we, in order to adjust it, we transfer X register's value F1 to A register, to the accumulator. Clear and flag to make the add with carry working properly, and then we add this 12. So now, after this operation, after this operation, we have X register equals to F1. After this operation, A register equals to F1. After this operation, A register equals to F1 plus 12. Or, well, I'm not sure how exactly it is, but actually F1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D. So, again, I'm sorry, so F1, F2, 3, 4, 5, 6, 7, 8, 9, 10. 10 is A, B, C, D. Yeah, so 1, 0, 1, FD. So after this operation, A register equals to 0, 1, FD. And we transferring this 0, 1, FD back to the X register. And now I'm starting at the absolute address of 100 hexadecimal where the stack page starts in K1, and I'm adding this relative offset that we have just calculated, and this is the exact location where the local variable depth in regards to the current stack frame is located. So how that makes sense? So after this operation, well, we have depth of 3. At this point, it's only 3. Being back to the A register, so we kind of restored the value that we had here. But since we have a whole lot of things here, yeah, we just lose the value in the A register. So we restore it back. Then we compare it with a 0. So in case of it is equal to 0, that's the condition to escape from the recursion. So self-explanatory, right? And if it is, then it jumps to return. And then it pulls back everything from the stack and returns to where it to where it was called from. But in this case, it's not the case, because now depth is equal to 3, so A register keeps the value of 3 here. So we subtract in 1, so this is like what is known as depth minus 1, and then we call in search recursively again. And now the next step is to see how these local variables are mapping onto the stack, formulating those stack frames, so that for every depth we have local instances of these variables that are needed. That's very essential. So just to demonstrate you that, so just get rid of this break here, and here I just add a couple more debugging lines of code. So for instance, we can say compare depth with 0, 2, right? Or even let's start with the 0, 3. Let's start with the 0, 3. We've been there, but anyway, and branch equals to break, and break is just a debugging label here, just to stop the execution and being able to inspect things. Assembly and upload in 0200 run. Now it should be exactly the same hex dump as we've just seen. So 0x 0x02. All right. Yeah, so this is the address. So bear in mind the little ending byte order in 6502. CPU, so 0205. So this should be read as not 0502 but 0205, so 205 hexadecimal, and that's the address of the initial call to the search. So it's called here, and remember this address because when it's gonna be called from here, the address is gonna be different. So let me make it always on top, right? Then, actually here we have a way more clear way of stack representation, because this snapshot is more accurate basically. So we put the address where we're calling the function from. So this address is put onto the stack. Then the first variable to put onto the stack is the search depth. So here it is. And then this FF, the best score initialization, it just claims the end of the stack. And here should be exactly 11 variables. So actually, no, 12 variables. So 1, 2, 3, 4. So this is the stack frame. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Exactly the number of pushes that we made here so far. All right. So then this is it. So then let's inspect the stack when the depth is equal to 2. So just to give you an idea how the stack is going to change after. So upload 0200 and hex dump 0x, and here we go. So now this is getting even more interesting. Make it always on the top. So now here is the stack frame for initial function call, and the initial address the search was called from is 0205 or 205 hexadecimal. But here the address is already different, so 022f. So 022f is this address. This address is 022f. So just to make sure that is the case, jump to subroutine stands for opcode 20. So just to make sure it is so. So let me just say 022f. Maybe one after or maybe one before. I'm not really sure. Hold on a sec. Okay, guys, I'm sorry. Just told it a little bit wrong, a little bit fooled you. I'm sorry for that. So just to bring a little bit of a clarity. Well, to be honest, I'm not really sure. Yeah, probably where I was wrong. So actually, 0205 is the address next after the function call, not this address. So one more time. So if I go to 0200, and so this is clear decimal flag, load immediate data to a register of the value of 3, and then here 20 stands for jump to subroutine. So 0203, and then we have the little endian address. Yes, the little endian and the big, like the lowest, and then the highest address. All right. And then we have the break. So it kind of points to the very last byte of the address of this subroutine call. So if we say 022f minus 2, it would be 022d. So 022d, and we have this function call here. So it kind of points to not the beginning, like I said. I'm sorry, it doesn't point to the beginning. It points to the last byte of. So this search. So this opcode is one byte. This label is 2 bytes because this is the absolute addressing mode. And the last byte, or the highest byte, the high byte is the last byte, is where it's pointed. So I'm not sure. Yeah, probably that's the nature of the 658. I don't remember exactly this, but it doesn't matter. So just want to give you an idea that this is the initial, let's call it the initial address where the search routine was called from, or better to say where to return, the address where to return from the search call. So that if we increment the next one, increment the program counter by 1, then we would be at the next instruction to execute. Yeah, that's the case. And here already we're calling this exactly the same search, but from the other place, which gives us a clue that we actually do this recursive call already. And note that first we have only one stack frame, and now after we're inspecting this already for depth too. So already 2 stack frames has been created. So all those 12 values for local variables are there. Know that the first byte after the address, so here is the address, here is the address, then the first byte after the address, remember this is the search depth, which is here, and the last one is the value for the minus infinity, and then the key and round functions. All right, so now we have 2 stack frames here, right? And now we go even further on, and yeah, and by the way, 00F2, and the stack pointer is now pointing to E3. So yeah, I already closed it down, but it's like 2 frames to the left, let's say, or 2 frames down. All right, so one last experiment might be like this. So when the depth is equal to 1. So now I want to assemble this and upload and 0200 and run, and let's have a look at the hex dump. Okay, all right, and here we go. So now we have 3 stack frames. So this one, so the depth is 3, then the depth is 2, so this is the second stack frame, and then depth is 1, so this is the third stack frame. And there would be one more, if we do the following thing. So actually, if just to show you the snapshot for snapshot of memory dump, in case when we compare into 0, so we're in the leaf node and actually want to return, but before doing all of these things, before actually returning, before pulling things from stack, which would make stack look a little bit different, so before any pull job, I just want to say, well, actually, yeah, let's just cheat a little bit. So instead of branch equals to return, just say branch equals to break, like this. So assemble upload 0200 and hex dump like this, and here we go. So now we should have up to 4. So this is the first frame, this is the second frame, depth 1, the third frame, and here we have the depth 0 and the fourth frame. All right, so that's how we make sure that that the recursion actually works, and to make sure that after all of this has been done, so we need to make sure that we do return all the things here properly. And somewhere in between, I would also put the evaluation. It's probably just right before the return to store the score. But for now, it doesn't matter that much, really. Or maybe not sure how exactly I'm going to be doing this, but not the case at the moment. So let's restore the code back. Restore the code back, and now so what's going to be happening then? So we're already here, so it's depth 0. Well, actually, I could have showed this in reverse, but that would be the same part of the stack might be not looking that probably, because again, I'm not 100% sure how exactly the development environment is, because again, the state of the emulator and the state for breaking the debugger might be a little bit different. Okay, forget that. So let's better just 0200. So let's run again. So we ran through the entire thing recursively, and we got back. Well, actually here. So we got back from this function. Now to make sure that all the pulls were made successfully, we can expect the F2 to inspect where the stack pointer is pointing to, and the stack pointer is pointing to the top of the stack back again. And again, we already seen the hex dump, so it might not be that perfect. But anyway, So actually, it just, yeah, probably, well, I'm not sure. Sometimes it just, this garbage kind of like is there. If I did this only for depth 1, then I'm not really even sure if this would be. So I've been experimenting a lot, and currently I don't even remember really how exactly it behaves in a different situation. Probably if it's not too big, it's just getting overridden by the KIM-ROM return addresses or something. Well, can't say for sure, but this doesn't really matter that much. But anyway, and probably depends on the search depth as well, but doesn't matter. So what we've proved here so far is that we have a recursive function with a whole lot of local variables, and one of those, the depth, is actually being referenced once in order to get decreased and then to make this recursive call back. And now the question is, how do we return the value from the function? So this is interesting. So let's have a look at the C code. So you see, like, we do return the best score after the very end, right? So, and here, for instance, we say we found a better move, then best score is equal to score. By the way, score is absolutely global variable here. So let's consider that it happens that we found a better move, and let's consider that the best score for all the three for all the depth is the same, which probably is not going to be the case in the real deal. But anyway, let's just assume that. And I just want to show you. I just want to change. So let's say we jump into the search, then we return, and for each depth on every stack frame, there would be different values for the best score. Now, to actually alter the best score somehow, so here I just want to alter the best score manually. So what am I going to be doing for that? Just want to use this part. So I want to put the value of the stack pointer to the X register, transfer it to the A, clear carry flag, add 1. Well, actually, here, instead of adding 1, and instead of dealing with all of this, I can just make 1 increment of X. So that should be fairly the same to point here to the best score. And then let's load some random best score. Let's make it 23, for instance. Let's call it like best score found. And I want to say STA 100 hexadecimal with an offset of X. And I want to store best score. And this is actually gonna be serving as the return value. This might sound a little bit weird, but let me demonstrate you that to give an idea. So 0, 2, 0, 0, and I run. So we're interested in the very eventual result of what this search function returns. And why are we interested in that? Because we need to make sure whether this is the maiden score or not. Because if this is the maiden score, then we're no longer searching. So we just end the program there at that point. So let's have a look at the hexadem again. All right. All right. So yeah, this is it. So you say like FF turns to 23 because we do set that manually. So it's no again like in the real engine. So here it might be like one value, here another, but the eventual value. What I want to say here is that the eventual value that we want to return. So like the one that we take from here, assuming that this is the final return. So the final return actually has the absolute address. It can be referenced by the absolute address, like 01F012, 01F2. So here, if I go to 01F2, we have this 23. So I can use this address to reference. So let's say here. I'm done with the search. So what's the return value? So here, for instance, I can say LDA 01F2 and then break. And then after this program executes, the return value of this function is going to be stored into the A value. So let me demonstrate you that quickly. So upload 0200 run, and 00F3 is machine context for the A register, and it's equal to 23. So we're done. So we just made a recursive function call, and we have returned the value from this. That's it from my side, guys. I'm sorry for this bit, for this being a little bit messy. And again, probably for real implementation, I'll get rid of this numerous pushes and pulls, because I think I can just adjust the stack pointer, because I don't essentially need these variables to be initialized to 0, right? Yeah, it's not essential. They can be like if you have a look at the implementation, then I do initialize temp source and temp destination, but even this is not necessarily needed. So only the best score should be initialized. The rest, like this mode generator variable, they can be just defined, and that's it. We don't really need to initialize them. So yeah, and since we don't need to initialize them, then I think that I can just manually adjust the stack pointer, like using something like this. So yeah, let's see how that goes. So yeah, this is it from my side. Please let me know in the comments below the video, what do you think about this fancy recursion in 6502, and thanks for watching. Until next time, and take care.